This morning I will be trying to set the scene with some high-level issues around why we're even trying to control greenhouse gases, where they come from, and what we can do about it. So the first thing is, why does climate change matter at all? Why is there this political urgency around the world to reduce greenhouse gases? And basically, the basic premise is, if the climate changes, it will cost money. It will actually cause economic disruption in many societies. So if we don't tackle climate change, it's going to cost us. And it will cost us more than if we do try and avoid it. So if there is climate change, we'll have to adapt to it. And that adaptation won't be cheap. If we can avoid some of the worst of climate change, it will be a cheaper option than just not doing anything. So it is an economic option, really, to say, if we don't do something, it will cost us a lot. If we do something, it will cost us a lot, but less than if we don't do anything. And just on a New Zealand perspective, will it affect us, or is it just something that affects the rest of the world? Now, here is some modelling that was done for the Royal Society. When it uses these global circulation models, which try and mimic the climate, to predict what the climate could be in the future. They're all models, they have some uncertainty, but presently our models are being uncannily correct in predicting what is happening to the temperature at a global scale. But these are downscaled to New Zealand. So just a couple of key parameters that might affect agriculture, particularly grass growth. That would be the simplest one. If we look now, most of the country has less than 40 days above 25 degrees centigrade. That gives us a very benign climate. On the east, you get more. In the north, you'd get more. A place like Palmerston North, it's about 15 days. But if we fast forward to 250, so what you start to see is that large parts of the country are moving up to this 40 to 60, 60 to 80 days above 25 degrees. And I don't know what it was like in other parts of the country, but 2 years ago in the Manawatu, we had over 40 days of 25 degrees or above. And that caused a lot of consternation in the sector in terms of growing grass, and we had some real problems around farm productivity in those years, simply because it was too hot. It was obviously dry at the same time, and it caused a disruption to productivity. And you can see that we would not farm in the same manner if that change does become true. If we fast forward again to 2100, and the further out you predict, obviously the more uncertain any predictions are, but you're now talking about in excess of 100 days for parts of really quite large parts of the North Island. You're talking about us moving from a benign temperate climate to a subtropical climate across nearly the whole of the North Island. And so, yes, they're predictions, but they're the reasons why people are wanting to act on this. It affects everyone. It affects the globally and locally. So, this is not something that politicians and scientists feel that you can ignore. Now, alongside the temperature predictions, well, what happens to water, the other great driver of growth, and probably an even more important issue for many? What are we going to get? If you look at this, it's increased runoff in some areas, reduced runoff in others. Again, different flows in rivers, which not only affects agriculture, but affects things like hydroelectric power, etc. But this is all driven by generally being wetter or keeping just as wet in the western parts of the country, but getting much drier in the east. And we're already marginal in many eastern areas. But perhaps the biggest issue is around the frequency of drought. I know it's a little bit small, you might not be able to see this, but most of the country here is down the bottom end. Large parts of the country where a drought is a 1 in 10 year event, maybe a bit more for some areas. But if you look going through here, this is 240, this is 20 years' time. Parts of the country are going to be in drought once every 5 years. That's the prediction. So you're seeing these increased temperatures, decreased rainfall, which does have severe implications for how we farm and the type of farming that goes on. So this will affect New Zealand. Now, we can argue about the magnitude and how accurate these forecasts are, but every forecast you see is we are going to have a changed climate. And that changed climate will cost. because there's always a cost to you. Every time we have a drought, they say how much that's cost the sector. Every time we have a flood event, how much does that cost? So, these things cost money. They're not something you can ignore from any government perspective, and the sector will have to learn to live with this or adapt to it. But what the issue around reducing greenhouse gases, it's trying to reduce how much you would have to adapt to this changing climate by tackling the climate itself. And then, okay, I've given you what the consensus climate view is. This is it is going to change and we're going to have to do something about it. There are some people who would argue against that. So what are the main arguments? Now, I could go on all day about the arguments against climate change and the rebuttals that I could make for those, but I'll focus on three things. And the first one, the climate isn't warming. Some people outright say, no, it's all wrong, the climate isn't warming. Second one, okay, we'll agree it's warming, but it's not man-made greenhouse gases. They're at such low levels in the atmosphere. How can something that's there at 1.9 parts per million, like methane, change the climate? Surely that's all wrong. And the third one is, well, in actual fact, methane only lives in the atmosphere for about 12.5 years. It doesn't matter. It keeps disappearing. Doesn't matter. Okay, so I'll tackle these one at a time. Here is the global temperature graph coming from around 1850. Now, as you can imagine, the further back, the less accurate the temperature records are. And we have very comprehensive temperature records from the 20s. But as the time has gone on, obviously, we have more comprehensive temperature records. But we also have proxies, tree rings, etc., that we can build this record from. And I think it's hard to argue now that the temperature is not showing an upward trajectory. This is the best information we have. This is from land-based measurement. We now have satellite-based estimates because the satellites don't directly measure temperature. You have to infer temperature from them. And the satellite data, which is only relatively recent, lines up incredibly well now with the ground-based temperature measurements. So I don't think it's possible for anyone to argue that we're not seeing an upward trend in the temperature. And we'll see, in the last 20 years, we've had something like 17 or 18 of the warmest years in the climate record. So to argue that the temperature isn't increasing would seem to be somewhat perverse in my view. Okay, so can I rule that one out? The next one, well, okay, yes, I'll accept it's warming, but is it greenhouse gases? Now, the first, the idea that greenhouse gases can change the temperature is not new. There is a Swedish chemist in the mid to late 1800s, Arrhenius, came out that carbon dioxide increments in the atmosphere would cause warming. That's 160 years ago or something like that. So the theory around this has been known for many, many years. And so what we have done is that with our knowledge of atmospheric processes, we have developed models that are completely driven by greenhouse gases. And those would be the main greenhouse gases, which would be nitrous oxide, methane, and carbon dioxide. And we also put in things like sulfate aerosols, which actually cool the climate. And so we have models that are predicting what's happening. So one test of whether the climate is being driven by greenhouse gases is to look at how well our models line up with the actual temperature. And they're uncannily good. So that's that same temperature graph. And so we look at our models. And that's the model called MAGIC that my colleague Andy Reisinger and I use. And this is one of a number of global models. I've just put one of them up, and they're all pointing in the same direction. And this is our model. This model is driven completely by carbon dioxide, methane, nitrous oxide, and a couple of other odd ones, and sulfate aerosols. It also has clouds built into it, which is quite difficult. So it's very roughly 1 degree above where it was prior to the 1850s. And that's when we started pushing out greenhouse gases from industrialization. The Industrial Revolution started a bit before that, but the quantity of greenhouse gases being pushed into the atmosphere then was quite small. So the temperature record really starts from the 1860s. And so the models we've got do exactly the same. They've obviously tried to put in greenhouse gases from that time. They put in the time series of greenhouse gases and say, what would we predict the temperature would be given those greenhouse gas concentrations? So the model is driven by greenhouse gas concentrations. And I think the models, and this is only one, I can show you half a dozen, and they're all predicting exactly the same thing. They're predicting what is happening in practice. Now, yes, they're not great at predicting any single year, but they're very good at predicting the trend. So the idea that it's not greenhouse gases seems to me to be not borne out. We've got a body of theory which says that because of the blanket effect, the temperature will go up. We've now got models that we can put all those processes in and predict what's happening, and our predictions are coming true. So it's hard to argue that greenhouse gases are not driving that change in climate. And we can also, from isotopic signatures, show that it's human-induced greenhouse gases. So the isotopic signatures of things like carbon dioxide and methane, we can tell where they come from. And it's not some natural process that's driving the increase in greenhouse gases in the atmosphere, it's human activity. So again, I think we can say, obviously there's always uncertainty in science. There's never such thing as it's 100% true. But I think we can say with very high confidence, greenhouse gases produced by human activities are influencing the climate. The next one is, well, hang on, methane, short lifetime in the atmosphere, about 12.5 years. After 50 years, you have very little of it's left. If I put a ton up today, very little would be left in 50 years. About 2/3 is gone in 12.5 years. So why does methane matter at all? Well, I have to resort to modeling. And we've got, in our international agreements, currently we've got this Paris Accord, which is trying to keep the increase in global temperatures below 2 degrees. Actually, the phrase is well below 2 degrees, but doesn't quantify quite what that means. And we've now got a goal of trying to keep it at 1.5 degrees. So what happens if we say, well, methane doesn't matter. Let's keep methane out of the equation. It's a short-term gas. Can we meet these global temperature goals? So what I've done here is to say, we've got the temperature goal, which is about 1.8. So you could argue it's well below 2 degrees. It's not down to 1.5. And then we know from the behavior of the gases, and I'll cover this, that we need to get these long-lived gases like carbon dioxide down as quickly as possible. So in this model, we've actually got carbon dioxide down to 0 by about 280. That means we've got to start taking carbon dioxide out of the atmosphere. We've got to reduce emissions from transport, energy generation, etc. And what we've done here is say we'll reduce methane emissions by about 1/2. And most of that reduction coming from methane that arises from fossil fuel extraction. Natural gas and oil, when you drill, you do get some emissions of methane which you can't control. And so we have attacked methane, we've severely attacked carbon dioxide, and we've met the temperature goal. Okay, so what happens if I don't do anything about methane? So what we'll do here is stabilize methane. So we're not going to get it down. We'll say, just try and keep them where we are. Well, we can actually meet the 2-degree goal. But what we have to do is get carbon dioxide down to net zero by 2060, roughly. And from then onwards, it has to go negative. So yes, you can meet the temperature goals without touching methane. But if you do that, it means you've got to get carbon dioxide down to 0 and then start pulling carbon dioxide out the atmosphere. We do not have the technologies to actually meet that goal. We do not have the technologies at the cost or scale that would happen. Okay, so then I'll say, okay, what are the implications if we can, that's about methane by about 1/3. That's when we're looking at agricultural methane. We're really pushing agricultural methane. It's not all stopped, but we've pushed it down a bit more. And what you see is that we don't have to get carbon dioxide down to 0 for another 80 years. And then we don't have to go negative. So yes, You can ignore methane if you wish, but if you do, you're going to have to knock out carbon dioxide, and we don't actually have the technologies to do that. So if we ignore methane, we will not meet those climate goals. And in actual fact, I haven't put the horror graph on here because predictions for methane are that they won't actually stabilize. They will keep going up. If we continue as usual with the pledges that countries have made in their nationally determined contributions, methane is likely to rise. And what that does, it brings another graph down here that says by about 2040, we have to have net zero carbon dioxide emissions. And no one knows how to do that. And from then onwards, you have to severely take carbon dioxide out the atmosphere. So if we ignore methane, there's no way that we can see at the moment that we'll ever meet our temperature goals because it's it is a very strong forcer on the climate. And there is no way we'll meet our temperature goals if we ignore methane based on current technologies and knowledge. So I think we do have to look at methane. It does matter if we are wanting to meet the climate goals that we've set. We can go back in the climate record using proxies, either ice cores, tree rings, and whatever, and we can construct a time series that goes back many, many thousands of years and even millions of years. And what we can't find, and I'll go back to this one, is anything where we are getting such a rapid rise in temperatures over such a short space of time. Now, we have seen fluctuations, as you do, but certainly in the temperature record we can construct, actually for at least 1 million years, we can't find anything equivalent to this. We can also find in the temperature record that there are some small exceptions, but in general, elevated greenhouse gases always end up with temperature rises, but we have not seen anything on the scale that's happened here. Just on carbon dioxide. Now, I came to New Zealand in 1990 to work on an experiment that looks at the effect of elevated carbon dioxide on pasture growth and on animal production. We started measuring carbon dioxide in the atmosphere out at Flock House, and the levels were 362 parts per million. Now, out at Flock House, they're about 410 parts per million. That's gone up 50 parts per million in 30 years. We've never seen that sort of rise over that sort of timescale in the recent climate history. But you're right, I mean, there are always issues. How long a timescale do you need? How do you know it's not some natural phenomenon? Now, there are things called Yankovic cycles, which there are varying estimates as to what they are, and we will have another ice age, because there are cycles within planetary orbits that will cause the temperature to cool and warm. We are currently, from what we can understand of these, we're in a cooling phase. We should not be warming, we're in a cooling phase. We came out of the ice ages around 15 to 20,000 years ago. Like the UK didn't have a population 15,000 years ago because it was covered in ice. It had come out of that, then was repopulated. It was populated before about 25,000 years ago. It was populated, they had to get out of there. And we're actually in a cooling phase now. We're not in a warming phase. So this is going against these longer term cycles. And so that's the argument with sunspots. We should actually be cooling, not warming. So a lot of that has been taken into account. As I said, in any scientific endeavor, you can never say 100% that's happening. What you can say is we've got a good theory, we've got evidence that's supporting that theory. Okay, so why is it such an issue in New Zealand? Yeah, that's a global picture. Yes, the climate's warming. Why are we in New Zealand? This little country down at the southern tip of the world produces 0.17% of the greenhouse gases. Why should we bother? Why is it a concern to us? Well, obviously we're a big trading nation, etc., and we rely on our international trade. But where it comes down to for us, and particularly the agricultural sector, is if we look at a typical developed country, the vast majority of their emissions come from industrial processes, energy generation, etc. And the biggest gas is carbon dioxide. So for the whole of the developed world, it's carbon dioxide. For New Zealand, methane it sits alongside carbon dioxide. They're roughly about the same quantities of carbon dioxide and methane are emitted from New Zealand. That's so unusual. If I looked at that profile and looked around the world, can I find another country that's got that? I'd have to go to Uruguay, Argentina, Chile, because we are so unusual in the developed world as being an economy that's still heavily reliant on agriculture. Hence, when we're talking about reducing greenhouse gas emissions, the agricultural sector, gets pinpointed. And so, in a typical developed country, as I said here, 80% of the gases are coming from energy, transport, agriculture. New Zealand, we about what we call carbon dioxide equivalent emissions, 48% comes from agriculture, which means that if we are making international commitments, it's very hard to meet those commitments without doing something about agriculture. If you say we don't do anything about agriculture, the burden falls on other sectors of the economy. Hence why agriculture gets in the spotlight here. It's not only that agriculture is changing its emissions. If you look at the transport sector, emissions have risen very strongly. Agricultural emissions have risen at a slower rate, but just the sheer size of the ag sector compared to other sectors means that there's always a strong focus on agriculture in New Zealand. Now, one very important thing is what's actually happening in the future. Because if we're thinking about reducing emissions from agriculture, you have to think, well, what's our starting point? What do we have to reduce them from? Where is our profile of emissions in the future? What's it going to look like in the future? And you look here, it's very, very difficult to predict what the emissions from any sector are going to be. As you can imagine now, we don't have subsidies, our sector is driven by market forces. And what are those drivers going to be in the future? In the past, this is 1990, and this is the date at which we have started estimating our greenhouse gases from, because that's part of our international commitments. And so from up until about 2005, we had this beautiful, nearly linear increase in emissions. And a lot of that was driven by a conversion, in many instances, from sheep into dairy. We got the rise of the dairy sector, and emissions started to increase. But then around about 2008, we got this drop. A lot of that was due to a big drop in sheep numbers triggered by 2 years of drought in the South Island and parts of the North Island. And since then, it started to move up, and that's where we got on this other linear track again. But where are we going to go? And this is really difficult. In 2013, and these are government predictions that they do in conjunction with the industry, is that we were going to be just on this lovely linear trajectory. We were going to move from about 40,000 kilotons to 45,000, an increase of about 12-13%. And then by 2015, it's not going to be quite like that. We're going to move up less. And then the latest prediction, which we published prediction, is that, hang on, they've stabilized in agriculture. We're not actually going to increase at all. Now, it's a little bit opaque as to how these numbers are calculated, but they're based a lot on international prices and international demand for our products. There will be a new forecast comes out at the end of this year, the 2019 forecast, and I think I haven't seen it yet, but I think it's going to affirm this flattening out. So that means that when we're looking at say, how difficult it will be to mitigate emissions, to bring them down is a lot below any given date now is a lot easier if this is the projected trajectory without any measures to reduce emissions than if it was going like that. So in actual fact, emissions in the agricultural sector peaked around 25, 26. So they're not going up a lot anymore. And a lot of this will depend on things like how much land gets converted to dairy, what fertilizer we use, etc. And I think with some of the other constraints coming on farming, I think you're probably likely to see that this is not going to be an upward trend as predicted previously. So that makes in a sense, the task somewhat easier than it would be as we thought in 2013. And just to show, although we talk about the sector has increased its emissions since the early 90s, there have been some very clear trends that's happening in the sector. And I'll just use the dairy sector as an example. What's happened here, if we look at the number of dairy cattle, it's gone up nearly double. And this is probably now tailing off. It's keeping flat, but this was up to about 214. If we then look at the amount of milk solids produced, the total up here. So we've about doubled numbers, but we've got nearly 3 times the amount of milk solids, which then shows how we've got an increase in milk production per cow, which is the green line. So we've got total increase in milk solids, an increasing milk solids per cow, total milk goes up. But if you look at our greenhouse gases, which is the blue line, they've also been going up. But this is the total emissions of greenhouse gas from dairy. But they've been going up at a slower rate than the total milk production, which means on a kilogram of milk solids basis, our emissions have actually been going down. We've become more efficient. Farmers have actually been making a contribution to keeping the lid on emissions by improving their efficiency. The problem is that we've increased the size of the sector quicker than we've increased the production efficiency, so emissions have gone up. If I put a graph up here for the sheep sector, it would be very different, because what the sheep sector's done, it actually now produces about the same amount of lamb from 22 million less sheep. Nearly 30 million less sheep. We used to have 57 million sheep in 1990. We now have, 25, 26 million, something like that. I haven't seen the latest data yet. But we produce the same amount of lamb. We used to get 0.95 of a lamb per ewe. We now get 1.3. I think the average figures nationally are. And so what's happened in the sheep sector, emissions have come down. Absolute emissions have come down by about 30%, because what we've done, we haven't increased production, we've increased efficiency, so our total emissions have gone down, and our emissions per unit of product have gone down. So those efficiency gains are very, very important when it comes to how we tackle greenhouse gases. And I've got a graph to actually demonstrate that. If we hadn't improved efficiency across the sector, this is for New Zealand, this is what our greenhouse gases would have looked like. Because of these efficiency gains that have been made across the sector, this is what our agricultural emissions look like now. And if we look at our emissions per unit of product, they've been coming down across the whole sector. Now, it's not just a New Zealand phenomena. I've got graphs from the world for every single product from the 60s onwards, and you see a trend in reduction in emissions per unit of product in every product all around the world. We're a bit faster than the average, but that just is a testament to the efficiency in which we farm, and that has been going up continually. Haven't gone back before the 60s, but I suspect that it's just a trend for millennia, really. But the idea that farmers aren't doing anything is wrong. They are doing something and have contributed via this efficiency gain. They may not have actually realized that or deliberately said, this, what I'm going to do is have an influence on greenhouse gases, but their actions do have an influence on greenhouse gases. And they point the way to how we can perhaps mitigate, because efficiency gains are going to be a very important component of how we tackle the greenhouse gas issue. So, the size of the mitigation task. What is the agricultural sector going to be asked to do? Now, this is somewhat of a movable feast, because we still have legislation. The Zero Carbon Bill was introduced back. It's going to be introduced back for its second reading soon. There was a select committee report, and there are still negotiations going on around what targets the agricultural sector is likely to face in the future. And at the present time, these are the different targets you'll see around the place. Some of these are set in legislation, others have been indicative. So currently, and this is set in legislation, we have to reduce our emissions and across the economy 5% below 1990 by 2020. We are going to do that quite easily because we have enough forestry credits to offset our emissions. And we will meet that target. That's called the Kyoto target. It's the second commitment period of Kyoto. We took a voluntary commitment under that, and we're going to meet that. There's no concerns over meeting that one. But of course, the Kyoto Protocol is now finished. We're all signed up to this. 190, there's only 3 countries in the world didn't sign up to the Paris Agreement. And I think one of those has signed up, and 2 wouldn't sign, I think, because they said it wasn't strict enough. So it's a global agreement. So our voluntary commitments, and they are voluntary for every country decides what it will do. It's not compulsory or legally binding. What we have decided to do is reduce emissions to 30% below 2005 by 2020. And that is a commitment set in legislation. So we have this commitment, 30%, but you notice that the date has changed. Previously it was 1990, and now it's 2005. And if you look back to where our emissions were in agriculture, the peak was in 2005. So we're reducing from what might be a peak. From an agricultural perspective, we peaked then, have come down below that. So in some ways, our using a baseline of 2005 is somewhat more beneficial for the agricultural sector. But that's what we've got now, and I'll explain that later. But we do have this other indicative target of 50% below 1990. We're back to 1990 again, 50% below 1990 by 2050. It's a 50-50 target set by the previous government, and it's what they call a gazetted target. It's not set in legislation, but it's an indicative target. And that was notified in 2011. So we still have got that. Now we're looking at this zero carbon bill, which the government has promised it will implement it will get past legislation before the end of this year, if possible. And that has some different targets. We now, and I'll explain this again later, looking at separate targets for different gases, for sound science reasons. And the carbon dioxide and nitrous oxide are set to be net zero by 2050, because net zero means you will have emissions, but you can also have sinks for emissions, things like trees. But for methane, there is a reduction of 10% below 2017, so we have another different date, by 2030. So there is a separate methane target, and given that most of the methane comes from agriculture, there is some from industrial waste processes, that means that the agriculture sector really is seeing a specific target for it, rather than previously these being global economy-wide targets for the country. And then this is indicative target, this range, that 24 to 47% below 2017 by 2050. The Select Committee reported back on Monday, and all of these targets still were in the report. So it didn't indicate that these should be changed. There are obviously political disagreements over the size of this, but this is the first time where agriculture is getting something very specific for it in terms of its major greenhouse gas. Now, how this will pan out, we're still not sure. It has to go through the House. What will remain, who knows? But this is where the latest information we have. But it is a bit watch this space to see if this changes. To get the zero carbon bill through, the government does have the numbers, but it wants bipartisan support to stop any toing and froing in the future. So we'll have to just watch to see how it ends up within the bill. Just to say, we have to be very careful when we look at those headline numbers. 30% by 230, 50% by 250. Some of those are what we term point targets, i.e., I just have to hit that point by a certain date. Others are what they call budgets. And so you have to differentiate between a budget and a point target. And the 30% below 2005 by 2030 is a budget target. And these budgets are worked out to an international formula. So under our current commitment, we have to get 30% below 2005. So this is 30% below our 2005, this point here. But it doesn't just start in 2030. We just don't have to get there. We have targets along the way. So by 2021 here, we should be about 25% below, roughly, it's a very, very rough figure, below our 205. So it starts early. It's not just achieving it at a point in time, it's a budget over the 10 years leading up to that point. So basically, these are our predicted emissions across the economy, which are very roughly over that 10-year period from 221 to 230, are about 750 million tonnes. Our budget, based on that 30% below 2005, but using it as a budget over the period, is around about 600 million. That means we have to reduce our emissions or take responsibility for emissions by buying those emissions from somewhere else of about $150 million, 150 million tonnes. And just to give you at the moment, we've got $25 a tonne carbon price. So we've got, literally up to $4 billion worth of emissions to buy or to reduce domestically. Agriculture, at the moment, is just under 39 million tonnes a year. Even if it stabilises, it takes up around about 2/3 of that budget. So if we don't do anything in agriculture, this gap here has to be met by the rest of the economy, reductions in it, or we buy them offshore. So if we exempt agriculture, you end up with putting a great pressure on other parts of the economy. But this is a very stern target. If it was just 30% by 230 in a straight line from where we are, it wouldn't be that bad. But because it's a budget that starts in 221, using this quite complex international formula, it's a much stricter target. And if you in actual fact went in a straight line from where we are, and to meet that whole of that wedge of emissions, we would have to get to something very roughly 45% below where we are by 230 if we went down in a straight line from where we are to meet that budgetary commitment. Now, if we actually try and bring in those other targets now, interestingly enough, the methane targets, and I've actually, just for flexibility, I've translated that methane target into carbon dioxide equivalent. If we just, because that's a point target, it's not a budget. It's not a budget between now and then, it's a point target. So how we reconcile these budgets and point targets is still not quite clear yet. But if we went in a straight line from where we are, now to meet that combined target of net zero for the long-lived gases, 24 to 47% below for the short-lived gas methane, we would have to reduce our emissions down to here, which means they become 60 to 70% below where we are now, depending on the stringency of that methane target. But because of this separate target for methane, this is, it's a very big proportion of our gases now, and so we do have to separately get methane down. This is the old 50-50 target. This is the methane target. But what this is saying in a very complex way is that across the whole of the economy, we are going to have to get our emissions to about 1/3 of where they are now by 250. So comparing the current 50-50 with the proposed zero carbon bill, it's somewhat more stringent, but not that much more stringent. But because you have this separate methane target, the impact on the agricultural sector is somewhat greater. But we are going to have to see how this pans out in legislation. But the really clear point from this is that the agriculture sector can't ignore this. It is going to be a part of this commitment, and what happens in the agricultural sector will determine how much international units we have to actually buy, because it's hard to see how we can reduce these domestically with current technologies. This is what I did about the straight line. If we came down in a straight line between now and 230 to get to that 230 target, we would mitigate those emissions. But because it's a budget, we wouldn't mitigate those. So that's why it's a very stern challenge to meet that 230 target, which at 30% below 2.5 doesn't sound that bad. But because it's a budget, it's a much more stringent target. So how do we set these targets? How does the government go about setting them? And it's been very contentious. You've got people arguing it should just be a science issue. Unfortunately, the setting of targets like this is not just a science issue. It's partly economic, it's partly political. So when we're setting targets, the science comes in around considering that the greenhouse gases are different. They behave differently in the gases. That's why there's a differential target for the long-lived and the short-lived gases. But when we come to saying, okay, how stringent should our target be? It depends on the nature of our international agreements. It's not just a science issue. If you look at the Paris Agreement, there are things in there that say, well, yes, we have to set our greenhouse gas targets, but we have to pay regard to food security and food production. So that's something else you have to bring into account. That's not just a science issue. Also, there's a very firm agreement that developed countries will take the lead and take a greater share of the burden. So we're a developed country. We've signed up to an agreement that says we are prepared to take a greater share of the burden. So that is not a science issue, that's a political issue. So in setting our targets, we have to take cognizance of that commitment as well as the food security and food production commitment and some other commitments in there, particularly around financing. Again, when we look at a target, we have to look at what mitigation options we have and what the price of those options are. If we had a very cheap mitigation option in agriculture that said increase productivity and reduce emissions to zero, we would not be having this conversation about what the target ought to be. It would be a very stringent target because no one would care about the target. So the availability and cost of mitigation options also sets how ambitious your target wants to be. And that's not just a simple science issue. And we also have to look at the reduction relative to other gases. If it's cheaper to reduce in the agricultural sector or cheaper to reduce in the energy sector, you can easily place an unfair burden, or what might be termed an unfair burden, on that sector because it has options. If you have no options, you may well have a very different target to if you have economically feasible options in another sector. So this comes round to the availability and cost. Also, what about social consequences? The one, obviously, that springs to mind at the moment is that we can offset a lot of emissions of those long-lived gases by planting trees. But what are the social consequences of putting lots of trees around the country? You know, we've already got, this, 50 shades of green, being very concerned about pine forests taking over large chunks of agricultural land and having implications for local services, implications for local employment, etc. So if you're setting a target, that also has to be taken into account. What are the social consequences? In the electricity sector, there are proposals around reducing emissions in the energy sector to zero. But what does that do to the price of electricity? If you try and reduce them to zero, it increases the price of electricity in a very substantive way. And so things like that have to be taken into account by setting targets, particularly setting targets for individual sectors. And this global equity issue, who should really take responsibility? Is it the rich countries, or do we want everyone to take the same responsibility? So there's this issue of equity. So just to continue on that target theme, why do we in actual fact have a different target for methane? Why has this been potentially going to be put into legislation? Well, first of all, I want to explain the behavior of the gases and how they warm the atmosphere and how we use these things called global warming potentials. What we have are different gases, but how can you put them in a common currency so that when we talk about what are the emissions from New Zealand, compare those to how they've changed over time, what happens if carbon dioxide is changing at a different rate to methane? How do we actually judge one gas against the other? How can we put them into a common currency so that we can say New Zealand's emissions are going up or going down? So what we use are these things called global warming potentials. There are other metrics, but the global warming potential is the one that we use for international agreements. We use it for all our domestic accounting. And in that, we have this exchange rate between different gases. Currently, under international agreements, 25 kilograms of methane, of carbon dioxide is equivalent to 1 kilogram of methane. 298 kilograms of carbon dioxide are equivalent to 1 kilogram of nitrous oxide. So how do we work that? How do we get this exchange rate? And this is global warming potentials. So what they are trying to do is look at how individual gases warm the climate over a given time period. So what I've done on this graph is actually just compared warming from methane, about a kilogram of methane, to 30 kilograms of carbon dioxide. The reason why I've chosen 30 under the new, there's some new metrics being worked out, and the exchange rate between carbon dioxide and methane is likely to be 30 or 31. It's still not decided yet, so it will be changing. So that's why I've chosen 30 here. If I throw out a kilogram of methane, what's happening is that the warming it causes is high in a short term, but over time it drops off pretty rapidly. Carbon dioxide, on the other hand, if I put 30 kilograms of carbon dioxide up, which is about the equivalence, the warming is nowhere near as strong in the short term, but it continues for a long period of time. So what you have to do is to say, well, over what time period am I comparing these gases? So internationally, they've chosen 100 years. So we're trying to say how much warming does a kilo of methane meet to some amount of carbon dioxide over 100 years. And what this does, it averages it. So if I look at the area under the curve at 100 years, which is the red line, that area is exactly equivalent to the area under the curve of the blue line after 100 years. So that's it. They have the same average warming over a 100-year time period. And that's why they're called global warming potentials. But they are the average warming over a given time period. So roughly, over the next 100 years, 1 kilogram of methane will cause the same average warming as 30 kilograms of carbon dioxide. Now, there are some real issues with that one, if you think about it. In the short term, using this GWP 100 completely underestimates the warming coming from methane. Conversely, in the longer term, using this 30 kilogram, actually overestimates how much warming in the longer term comes from methane, and vice versa with carbon dioxide. Because the time frame differs very strongly. And so one underestimates it in the short term and the other overestimates it in the long term. And also, okay, what happens if you decided to use 50 years? You'd actually have a much bigger exchange rate, because to equalize the areas under the curve, I'd have to, because most of the methane curve comes within 50 years, I'd have to have a much bigger amount of carbon dioxide to get the same average warming. So if I did 20 years here, the conversion is about 85. So about 85 kilograms of carbon dioxide is the equivalent to 1 kilogram of methane over 20 years. So the time frame I choose is very important. Conversely, if I did 200 years, it would actually drop right back down here. It would be much smaller, the conversion. So you have to think how they behave in the atmosphere and over what time frame am I interested in. So globally, they've said, well, we're trying to get temperature down by the end of the century. We don't want it to go above 2 degrees by the end of the century. So 100 years is regarded as a relatively fair time frame. If we took it for the next 20 years, it would have issues around intergenerational equity. So because then the burden would fall very much on the current generation. So they've tried with 100 years to balance intergenerational fairness and the time frame over which we want emissions what you want temperatures to peak. Now, this is quite contentious. So you'll see arguments, oh no, we should use 200 years. Oh no, we should use 20 years. Depends which side of the debate you want to look at. But I think the 100 years is trying to be a compromise. But what you do see, the 100-year time frame overestimates methane in the longer term and underestimates what happens to carbon dioxide in the longer term. And I'll try and explain this here. And because the different gases do have different effects, and it comes back to whether they're short or long-lived in the atmosphere. So here, this is just for comparative purposes, I've given a pulse of an emission. So don't worry about the size. So I'm putting that out every day or every year, whatever time frame you want. I put an emission out. And this column here is methane. This is nitrous oxide. This is carbon dioxide. So if I put a unit of methane out, because it's short-lived, you get an immediate rise in the concentration in the atmosphere. This is concentration. But after around 50 years, you do not get any further increase in the concentration of that gas in the atmosphere. Because it's short-lived, it breaks down. I put a unit up in 50 years' time. A unit's breaking down from a previous emission. So they don't increase the concentration in the atmosphere because each unit I put up here is balanced by a unit that's broken down that I put up at a previous time period. So, and this is very important, the concentration is what drives the warming. And with methane, if I put a constant amount out, I no longer increase the concentration in the atmosphere. Warming then starts to tail off. You notice warming doesn't level off completely. That's because there are delay effects in the atmospheric climate. Easiest one to understand is that you warm the ocean. So if I warm the climate, I warm the ocean. But then the ocean can keep giving out heat for many, many years after the warming has stopped because it's a store of heat, just like a hot water bottle. You heat it up very quickly, but it will give you the heat over a long period of time. The ocean works in the same way. So even though I don't increase the concentration in the atmosphere, the warming continues for a little longer, but it starts to flatten out. After about 200 years, it's pretty flat. I contrast this with these two here. I'm putting a pulse out. Because they break down very slowly, each unit I put into the atmosphere just adds to the unit I put in yesterday or the day before or whatever. So over time, I'm just increasing the concentration of the gas in the atmosphere. And very much for carbon dioxide, it's virtually completely linear. And over a 200-year time frame, it's almost linear as well for nitrous oxide. So the concentration of these two gases, because they don't break down, increases each time I put a pulse into the atmosphere. And then I look at what does that mean for the temperature. It means that the temperature goes up in a virtual linear manner. So because the concentration is increasing, the temperature goes up. So the difference is this gas, its warming effect slows down and virtually is eliminated after a couple of hundred years if I keep putting a pulse out. These two, they're cumulative because they don't break down, and the warming is cumulative. So in the longer term, these two gases are much worse. Hence, we have to get these down to zero as soon as possible because their warming accumulates. This one here, we don't have to get them down to zero to stabilize the temperature. And that's why there is a very sound scientific argument that you treat the gases somewhat differently. So there's a couple of simple messages that come from that. If you want to stop additional warming, if you want to stabilize it, you have to get these long-lived gases down to zero. There is no other way about it because warming accumulates. We just have to have no more emissions. That will stop any additional warming. On the other hand, with methane, methane does not need to go to zero. You can get an amount that you reduce methane down and you do not add to warming at all. But because methane always warms the atmosphere, the less warming, the better. The less methane, the better, because it adds little to warming. But this is why we can treat them differently. And so you can have what you might term a more lenient target for methane to have exactly the same effect as a very stringent target for carbon dioxide and nitrous oxide. Hence, you're seeing net zero for 250, but somewhere between 24 and 47 for methane. It's because they behave differently in the atmosphere and their effect on the climate is different. So there's a very strong argument to treat them differently. We might debate as to how much you should reduce methane, but there is a powerful science argument that you don't have to reduce it by the same amount as you do with the long-lived gases. And just to say, well, what causes most of the warming in New Zealand? So we're putting out emissions, and just to think, it doesn't mean methane's off the hook. It means that you can treat it differently. But if I actually look at our emissions in 2016, how much warming will they cause in the future? And most of the warming for the next certainly 50 years, methane will cause most of the warming. So our emissions, these were our emissions in 2016. We have a smaller amount of methane, a large amount of CO2, very small amount of nitrous oxide in absolute gas terms. But what you see is this is the warming. This is put through that same climate model that we use to look at the temperature of the world. And you see the warming in the short term, in actual fact, really out for the next 30, 40 years. If the warming caused by our current emissions is much more for methane than it is for carbon dioxide, despite methane being quite small. So this is why reducing methane will reduce New Zealand's contribution to global temperature rise. So you can't ignore methane. And this is just a short video that in a sense covers some of the ground I've just covered, but in a much simpler way. And this is available on the website.
Kia ora. We're here to talk about climate change, how it works and how it relates on farm.
We'll also reveal New Zealand's biggest contributor to climate change. It might not be what you think, and it's rather close to home. Our atmosphere is a magnificent cocktail of gases, water vapour and particles that constantly mix and mingle. It gives us our oxygen, protects us from radiation from the sun and controls our weather. It's a delicate balance and all life depends on it.
But we're doing things down here which are really upsetting the balance up there. Human activities are rapidly increasing the concentration of greenhouse gases in the atmosphere. They're called greenhouse gases because they trap the heat and warm the planet. The main greenhouse gases that we produce are carbon dioxide, nitrous oxide and methane. Globally, carbon dioxide is the most important because it stays in the atmosphere a very long time.
Here's what's going on.
Incoming solar radiation warms up the surface of the Earth. The Earth's surface then sends this heat back through the atmosphere and most of it goes out into space. But some of this heat is trapped by greenhouse gases and this extra heat warms up the atmosphere. So, the more greenhouse gases we emit into our atmosphere, the more it'll warm up and affect our climate.
And it's already having a big impact. Earth's average temperature has warmed by about 1 degree Celsius since humans started using coal, oil and other fossil fuels. Globally, 18 of the hottest 19 years on record have occurred since the year 2000. Here in New Zealand, temperatures are about 1 degree hotter than they were a century ago. We're seeing more extreme weather, and that's before we start talking about rising sea levels, melting glaciers and polar ice. As our climate in New Zealand changes, it might not be possible to farm in the same ways or the same places as we do now. A couple of degrees of warming might not seem like much, but it has a big impact on crop and pasture growth and on pests and diseases. More extreme weather also creates bigger problems.
Now, it might surprise you to learn that New Zealand's biggest current contribution to this isn't carbon dioxide at all.
Nope, it's methane from animals. You can find out more about how methane affects climate change in our next video.
So what are policies? We can have targets for reducing emissions, but what are the policies the government is putting in place to reduce emissions? Not just in agriculture, but across the economy. And the principal policy lever the government has had, and successive governments have had, is the emissions trading scheme. And Phil will talk a bit more about the emissions trading scheme this afternoon. But this was meant to be an all gases, all sector scheme, but agriculture was never been introduced into that scheme. There have been a number of proposals to do that, but it has never actually been brought into that emissions trading scheme. Now, the emissions trading scheme, I think even by its supporters would say it's not been a universal success for a number of reasons. It never actually had an emissions cap, which an emissions cap forces, with the buying and selling below a cap, it heavily influences what the price of emissions will be. And so it never actually had a cap. There was, until relatively recently, unlimited ability to purchase international units. And New Zealand was the largest purchaser of units from the ex-Soviet Union. It brought a very large number of Ukrainian credits, and those credits were coming in at one stage at less than $1 a ton. And so that completely undermined the price of our emissions trading scheme, the price of carbon in the emissions trading scheme. As you can imagine, if you can buy emissions offshore at $1 a ton, you're not going to be paying much for a New Zealand emission. So it drove the price down. Now that loophole was closed, and we can no longer buy emissions units offshore. And you now see that the carbon price in the ETS is close to $25 a ton. At one stage, it was less than $1. And also, there have been special arrangements to in interest, decrease the burden on certain sectors, those that are called internationally competitive at risk, and such that there were special deals, including things like 2-for-1 units, so that you got units at half price. So these all weakened the signal coming from an emissions trading scheme. Now that scheme is currently being modified, and there are a number that have been leaked out or that were given out over time, and they will see quite big changes to the emissions trading scheme. The biggest one, in actual fact, is the introduction of a cap. And as I said, that combined with the inability to purchase international units will affect the price and affect how that emissions trading scheme influences behavior. And so what is the agricultural sector going to do? What is it going to be asked to do? What's the government's thinking of this? As well as my role in the New Zealand Agriculture Greenhouse Gas Research Centre, I am on the government's Interim Climate Change Committee, which was asked to look at whether emissions in agriculture should be priced and whether agriculture should go into the ETS. We came up and we were simply asked to do this one question: how would you best price units for agriculture? And we looked at a number of things. We looked at, well, can you have a voluntary approach? Would a voluntary approach be the best? Get the sector to agree voluntarily to manage down its emissions and not introduce legislation or a policy, let the sector do it itself. Our view of that was that there's, although it is a very desirable thing to let voluntary agreements happen, how does it have teeth? What happens if the agreement is not met? What happens if the sector is not managing down its emissions? And also bringing agriculture into the emissions trading scheme, because the government has the ability to auction units, it gives a fund that could be used to help the sector. If there was a voluntary agreement, where does the money come from to help the sector transition to the situation where perhaps emissions are priced on farm and every farmer has an obligation to reduce its emissions? And so we came out, we said, yes, there are some benefits to this, but we didn't think, because of a number of issues, we thought that perhaps it wasn't the best approach to guarantee emissions reductions. We had some people in sectors arguing that we should simply have limits, just as we have with water. If you can leak so much nitrogen, why don't we have a strict emission limit, i.e. you can produce X tons per hectare. That's it, you have to get down below it. Some organisations are arguing very strongly for that. The problem is, how do you set a fair limit at the individual farm level? What's a fair limit for every individual farm? How do you even calculate what the past emissions are to set the limit? And we discussed this with representatives from the sector. We tested across the sector, and there was very little support for this, the limit argument. It's very crude. How do you set a fair limit for everyone? It doesn't reduce emissions at least cost, which is a very important principle. So we came out against that one. What we then considered most seriously was whether you go, basically, do you put agriculture into the emissions trading scheme, and this is what we were asked to consider, or is there an alternative? Now, the two alternatives generally are, do you put a tax on emissions, or do you put it into an emissions trading scheme? They are very, very similar. People don't like taxes, but an emissions trading scheme is very similar to a tax. In an emissions trading scheme, you set the quantity of units that are available. You say, this is the amount of reduction we have to get, and then you trade to get that reduction, and the price changes. So you actually are guaranteed your reductions, but you don't know what the price is going to be to achieve those reductions. So that the uncertainty in the emissions trading scheme is the price of units to reach a given target mitigation point. In a tax system, you actually set the price, but you hope then that that price is set, that it brings the emissions down to where you want them to go. So the uncertainty in a tax system is whether that price is enough to bring your emissions down. So the uncertainty then is actually in the emission reduction, whereas the ETS, you know what emission reduction is, but you don't know what the price is. But they're both out to achieve the same goal. And they're very little different in operation, because in practice, interestingly enough, most emission trading schemes throughout the world have price floors and ceilings because they don't want the price to go too high. So they're never, in practice, free. The price is never free to move in any direction it wants. It tends to be controlled because you don't want the price to get so stupid that it causes viability of businesses to be questionable. We came out on behalf of this one. So the recommendation from the Interim Climate Change Committee was to go to what we called a greenhouse gas levy and rebate scheme. The reason why we called it a levy and rebate scheme was that within the coalition agreement, it's agreed that the sector will only face 95% of the, 5% of the liability in any pricing scheme. It would be exempt from 95% of the cost. But how you allocate this exemption can actually change what individuals pay. And so in our scheme here, with this what we call a levy and rebate scheme, depending on how you allocate the free units, some people would actually get a rebate and others would get a charge. On average, there'd be a 5% charge across the sector, but because of how you can allocate the free allocation, some people would in actual fact get a rebate. So that's why we called it a levy and rebate scheme. And that now it's being considered, this whole package is being considered. Just to finish off, there's this wonderful statements, and I've just been looking at some comments on websites, and this is coming up. New Zealand is the most efficient producer in the world. If we reduce our emissions by reducing production, what we do is in actual fact, other producers fill the gap and globally emissions will go up. So it's perverse, it's a perverse outcome. Because we're the world's most efficient producer, if we don't produce it, someone else will. They'll produce it with more greenhouse gases. So us taking on limits has this perverse outcome of increasing emissions globally. So the question is that a true statement? And it's a lot more complicated. Again, we had to look at this as part of our role as the Climate Change Committee. First thing is, we cannot say we are the lowest producer in terms of efficiency. There is just not the data to say that. We don't have standardized methods, etc. What we can say is that we are amongst the most efficient based on the data that we have. There are a group of countries, the US, most of the EU, they produce milk with about the same greenhouse gas footprint as far as we can tell. So this statement that we are the most efficient is actually not backed up by the facts. We just cannot back that up. We can say we're amongst a group of countries that are the most efficient. But our big competitors, and you have to look which market this is, if we stop producing milk for the Chinese market, the whole milk powder, who would produce it? Because that's the big question when it comes to this, what they call leakage issue. If it is produced by the Netherlands, California, Ireland, they produce with the same footprint as we do. So it would just be neutral. We would not be having this perverse global outcome. It depends who produces the product. If, on the other hand, it was domestic Chinese production, they produce less efficiently than we do, and it would go up. So the question's a nuanced question, is who would fill our gap? And the other complication is most of our competitors also have national targets to meet. Because a lot of our competitors are developed countries. So if, say, in Ireland, they expand their dairy sector to fill any gap that we have, it means because they've got a national domestic cap that they have to reduce elsewhere in the economy. So you can't just think of agricultural emissions. If they increase agriculture, they have to reduce industry or energy emissions. So again, there's not that perverse outcome you would think of because a lot of countries have caps. And in actual fact, it's quite interesting, that other countries may not be able to fill the gap. So I can quote from the Netherlands, one of our biggest competitors, particularly milk. They cannot really increase their production. They're working on, there will be no increase in production, more to do with they just can't, their water quality, and they just have got nowhere to put their waste products now. And so it's highly unlikely that there will be any increase in production in our competitors, well, certainly one of our major competitors, if we reduced our emissions. So there is limited scope in some countries to do this. And of course, if we have a 95% free allocation, there's actually very little incentive for us to reduce our emissions anyway. So by introducing a price on emissions, it's hard to see that we would reduce our production because the price signal is so low with a 95% free allocation, which is a coalition government agreement. And to argue that there isn't scope to reduce emissions in some farms and to some extent isn't true. So we can actually meet some of these targets with current technologies. So if I said that it definitely applies to the dairy sector, there hasn't been the work done in the beef and sheep sectors, and there is still some uncertainty, so a lot more work needs to be done about this, but the evidence we have says that this leakage argument, this perverse outcome argument, is perhaps overstated to some extent, but we need more evidence. So just to summarize, mitigating climate change will cost, but not mitigating will cost more. There's going to be strong pressure to reduce agricultural emissions simply because of the importance of agriculture emissions in our national profile. All greenhouse gases are not created equal. Methane is different, and we can justify a separate target for methane on science grounds. Agriculture is the only sector where there isn't a price on emissions. And so I think that's we're going to see that come. And it seems highly likely that there will be specific greenhouse gas reduction targets for the ag sector. A bit uncertain, but that's, I think, the state of play as to where we are now.